So looking back at discussions we've had about statistical significance and hypothesis testing, there's one concept that I think is really important but not particularly intuitive that I'd like to go through and talk about a little bit, and that's the difference between one and two-tailed tests of statistical significance. And so we're going to start with just sort of a initial crash course reminder refresher on what we're talking about when we're talking about statistical significance and hypothesis testing. So with hypothesis testing, we often begin the process by identifying what I call the threshold of weirdness. This is the point where we transition from that's not really that interesting or surprising to, oh my gosh, something's going on, right? And so if you flip a coin and call it in the air, right, that's not particularly impressive. It's a 50-50 shot. Nobody's going to be impressed by that. If you have a deck of cards and you say, I'm going to pull the two of diamonds, and you pull the two of diamonds, people are much more likely to view that as a magic trick, as something really clever or interesting was happening there. And so something's happening where we transition from no big deal, that's just randomness working itself out, to that wouldn't have happened by chance. And so statisticians have sort of set that level, typically by convention, at about 0.05 or a 1 in 20 chance. And so we'll call that maybe our alpha level. And that's how we'll think about hypothesis testing and statistical significance and all these things that we talk about all the time in statistics. But I want to flag briefly that flipping a coin and calling it in the air, or correctly predicting a card that you're going to pull from a deck, is a little bit different than hypothesis testing, right? When I flip a coin and call it in the air, I'm trying to get it right. With hypothesis testing, we sort of posit this null hypothesis, and we hope that we'll show that the null hypothesis is wrong. And while there's only really one way to be right when you flip a coin and call it in the air, there's lots of ways you can be wrong. And this ends up being relevant when we think about hypothesis testing and how it relates to the sampling distribution. So typically what happens when we're doing hypothesis testing is we begin with this sort of null hypothesis, which means essentially we don't know what's actually going on out there in the world. So we're going to begin from a position of skepticism and assume that our sampling distribution is centered on 0, 0 representing no difference between two groups, or no relationship in terms of correlation or slope between two variables. And so we're going to sort of assume skepticism, null hypothesis, sampling distribution is centered on 0, and then we're going to look at our sample and where our sample falls and ask, if I were to put my sample on a sampling distribution centered on 0, would that make sense? Would that be the kind of thing that would just happen normally with sampling variation? Or would something really unusual be happening, something that would maybe cross that threshold of weirdness, that 0.05? And so we could think about that in terms of these two different Bell distributions, about where you cross that threshold of weirdness, right? So in the top bell curve distribution, the shaded areas represent 0.05 or 5% of the area of the bell curve, but it's in two different tails, right? Essentially what we're saying is if you get a result that's really, really high or a result that's really, really low, both of those are going to represent ways to show that the null hypothesis just doesn't make sense, right? If you get a sample that falls out in that range, we're going to look at that and say that's really unusual and therefore unlikely, and therefore I'm going to reject the null hypothesis. But the second one sort of puts all of that 5% of the area on 1/2 of the distribution and essentially says, I don't have any reason to think that there's going to be anything happening on that left-hand side, and so I'm just going to ignore it. And when I think about what constitutes a bizarre result or a weird result or something that's going to be considered statistically significant, I'm only going to look here on the right-hand side of this distribution. And if I end up with a result that's a little bit past 1.651 for a t-statistic or a test statistic, right, if I might be at 1.7, I will conclude that that's sufficiently odd enough or weird enough that I can reject the null hypothesis. Well, that same test statistic of 1.7 wouldn't meet that threshold of statistical significance in the bell curve above, where there's a higher threshold for crossing that threshold of weirdness, where you would need a result of, I think, 1.96 to sort of reach the point where we're sort of in that gray shaded area where we're saying, wow, this is really unusual. And so this ends up being a fairly important philosophical and statistical question about what does it mean to invalidate the null hypothesis? What kind of a result would that look like? Now, in practice, most statistical significance measures that will be given to you by statistical programs like SPSS or Stata or SAS or R are going to give you p-values, the probability in those tails, for a two-tailed test. In other words, it assumes that what you're looking at is having the shaded areas in both of the tails being the zones that we're looking at for statistical significance. And that works most of the time, particularly if you don't have a strong hypothesis about where you should be seeing the results, whether it's going to be, a difference with one group being bigger than the other, or vice versa. If you're not sure if there's going to be a correlation, if it's going to be positive or negative, then working with a two-tailed test makes a lot of sense. But if you have a strong directional hypothesis, and there's maybe lots of situations where we would. So I study foreign policy and public opinion and those sorts of things, and there's a pretty well-established gender opinion gap where men tend to be more supportive of the use of military force than women, right? And I've seen that pattern play out in survey after survey after survey. If I start up with a new survey, I'm not walking in saying, I'm not sure, maybe in this survey, women will be more supportive of military force than men, maybe men will be more supportive than women. I'm going in with a pretty good expectation that men are going to be more supportive of military force than women based on all of his past experience and literature. And so I might not want to think about that in terms of a two-tailed test of, we could have bizarre, results on the left-hand side or on the right-hand side, and both of those would invalidate the null hypothesis. I might really only be looking at what's going on that right-hand side, expecting men to be more supportive than women of military force. And as a result, maybe I don't want to use that approach that's taken by SPSS and giving me my p-values that are for a two-tailed test. And so what I could essentially do is I could take those p-values and divide them by 2. So I'm essentially getting smaller p-values by looking only in one side of the tail. And that would be a way of rethinking my hypothesis test. But I'd really encourage people, if you're going to go this route, be very transparent about this. And the reason I'm saying this is when we opt for a one-tailed test of significance, we're essentially setting a lower threshold for what it's going to take to reach statistical significance. And again, if we flip back here, you would need to find a test statistic, a t-statistic greater than 1.96 to get into the gray area on that top bell curve. But on the bottom bell curve with the one-tail test, you could get a test statistic that just has to be larger than 1.651. And that's therefore allowing for things that maybe aren't as distinctively different from the null hypothesis to be flagged as statistically significant when they might not reach that threshold if we didn't have that strong prior belief that we would only be looking in this one side. So it's essentially a weaker, less strenuous test of statistical significance. And another reason why I think that that's particularly important is because it is really easy after you have sort of run your results to look at those p-values and say, oh, well, it's maybe not statistically significant with a two-tailed test, but it would be with a one-tailed test. And that's kind of what I had expected. And this is a form of a statistical cheating. And I think the metaphor to make sense of this would be if I flip a coin and call it in the air and it lands heads and I had called it heads, you're not necessarily impressed. But if I flip a coin in the air, wait for it to land, look at it, say, oh, heads, you're not only not impressed, you would view that as cheating of looking at the result after it's landed and drawing your conclusions based on that. And so if we're going to use one-tailed tests of statistical significance, we should have a very strong prior driving why that is. We should be upfront with people that that's what we're doing. We're using a one-tailed test rather than a two-tailed test because people might be expecting a two-tailed test. And we need to make that decision before we run our numbers so that we're not sort of mapping onto our results an explanation for why we should be using this less strenuous, less rigorous standard. But hopefully that sort of helps differentiate what we're talking about when we talk about a one-tailed and a two-tailed test.